Something just happened in our solar system that shouldn't be possible. An interstellar visitor from beyond our cosmic neighborhood has begun releasing objects into space, small, deliberate, structured releases that form patterns no natural process should create. Scientists are watching in real time as 3i Atlas ejects what can only be described as mini probes, and the implications are staggering. This isn't supposed to happen. Comets don't behave this way. They don't release organized formations of smaller objects with apparent purpose and precision. Yet here we are, staring at data that challenges everything we thought we understood about these ancient travelers from the depths of interstellar space. Stay with me through the next minutes, because we're going to unravel one of the most perplexing mysteries unfolding right now in astronomy. The strange case of 3i Atlas and its impossible ejections that have left some of the world's leading scientists questioning whether we're witnessing our first genuine encounter with technology from beyond Earth. Let me paint you the picture of what's happening up there, millions of miles away, in the darkness between worlds. 3i Atlas arrived from interstellar space, a wanderer that originated somewhere in the vast expanse beyond our sun's influence. These visitors are rare. We've only confirmed a handful of interstellar objects passing through our solar system, and each one generates enormous scientific interest because they carry secrets about other star systems, other corners of the galaxy we can never directly reach. But 3i Atlas is different. This one isn't just passing through quietly, it's doing something that's causing alarm bells to ring in observatories around the world. After its closest approach to the Sun, 3i Atlas began exhibiting behavior that defies conventional comet physics. Observers noticed jets, streams of material being ejected from the object, but not the kind of jets we typically see. These weren't the random, chaotic outgassing events that happen when frozen volatiles on a comet's surface get heated by solar radiation and explode outward in all directions. These jets were linear, organized, and perpendicular to the comet's trajectory. They formed an X-shaped pattern, a configuration so precise that it looked almost engineered. And the material being ejected wasn't just dust and gas. There were distinct, solid objects, small bodies being released in what appeared to be controlled sequences. Now, before your mind races ahead, let me be clear about what we know and what we don't know. The observations are real. Multiple telescopes have captured images showing these unusual ejection events. The data exists, and it's being analyzed by teams of astronomers who are trying to make sense of what they're seeing. But the interpretation, whether this is an extraordinary natural phenomenon or something else entirely, that's where the controversy begins. That's where scientists split into camps, where heated debates erupt in academic circles, and where someone like Avi Loeb, the controversial Harvard astronomer who's never been afraid to ask uncomfortable questions, steps forward with a hypothesis that makes headlines and raises eyebrows in equal measure. Avi Loeb is suggesting that what we're watching might not be natural at all. He's proposing that 3i Atlas could be deploying mini probes, small reconnaissance devices designed to gather information about our solar system. Think about that for a moment. If true, this would mean an artificial object from another civilization, perhaps launched thousands or millions of years ago, has travelled across the incomprehensible distances between stars, survived the journey through the hostile environment of interstellar space, and is now conducting operations in our cosmic backyard. It sounds like science fiction, it sounds impossible, and yet there's data that needs explaining, and conventional explanations are struggling to account for what's being observed. The reason this matters, the reason you should care about a comet millions of miles away doing something strange, is that it touches on one of humanity's most profound questions. Are we alone? The universe is unimaginably vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars, many of those stars hosting planets, some of those planets potentially harbouring life. The mathematics alone suggests we shouldn't be alone. But knowing something intellectually and having actual evidence are two entirely different experiences. If 3i Atlas is what Loeb suggests, then we're not talking about speculation anymore. We're talking about confirmation. We're talking about a watershed moment in human history when we transition from wondering if we're alone to knowing with certainty that we're not. But let's not get ahead of ourselves. The scientific method demands caution, requires evidence, insists on ruling out all prosaic explanations before entertaining extraordinary ones, and there are plenty of scientists who are urging exactly that kind of restraint. They're looking at the same data and proposing natural mechanisms that could produce these observations: fragmentation events, unusual outgassing patterns, tidal forces from the sun's gravity causing structural stress and breakup. These are legitimate hypotheses, rooted in physics we understand, explaining phenomena using processes we've observed before. The problem is, none of them quite fit. Each explanation accounts for some of the observations but leaves others unexplained. The jets are too linear, the timing is too regular, the X pattern is too symmetrical. It's like trying to force a puzzle piece into the wrong spot. You can almost make it work, but something's always off. This is where we find ourselves right now, suspended in uncertainty, watching an unfolding mystery in real time. Telescopes are pointed at 3i Atlas, capturing every detail, every change, every new ejection event. Scientists are running models, testing hypotheses, arguing passionately about interpretation. And in the background, there's this nagging sense that something unprecedented might be happening, that we might be living through a moment that future historians will mark as a turning point, the moment when humanity's place in the universe shifted from isolated to connected, from alone to aware of others. What makes this particularly fascinating is the psychology of it all. We're wired to find patterns, to see intention, to project meaning onto ambiguous signals. Our ancestors survived by being hypervigilant, by assuming that rustling in the bushes was a predator rather than wind, by erring on the side of caution when interpreting uncertain data. That same cognitive machinery is at work here. When we see organized patterns in space, our brains immediately jump to design, to purpose, to intelligence. It's a bias we have to be aware of and compensate for. But it's also a tool that served us well. Sometimes the rustling really is a predator, and dismissing genuine signals as noise can be just as dangerous as seeing patterns where none exist. The truth is, we're in uncharted territory. Interstellar objects are new to us as observable phenomena. We only detected our first one, Oumuamua, a few years ago, and it also exhibited strange characteristics that sparked similar debates. Now we have 3i Atlas presenting another set of anomalies, another collection of observations that don't fit neatly into our existing frameworks. Maybe this is just what interstellar objects do. Maybe they carry compositions or structural properties that we haven't encountered before, because all our previous comet experience comes from objects that formed in our own solar system. Or maybe, and this is the possibility that keeps astronomers up at night, maybe we're looking at something fundamentally different. Something that requires us to expand our categories beyond natural and artificial, to include possibilities we haven't even imagined yet. Here's what I want you to understand as we dive deeper into this mystery together. Science thrives on anomalies. Every major breakthrough, every paradigm shift, starts with observations that don't make sense, with data that refuses to be explained by existing theories. Anomalies are uncomfortable. They create tension. They force scientists to question assumptions and reconsider frameworks they've spent careers building. But they're also opportunities, chances to learn something genuinely new, to expand the boundaries of human knowledge into territories we've never explored. And 3i Atlas, with its impossible jets and mysterious mini-probes, might just be one of those opportunities. So here's my challenge to you. Watch this evidence unfold with me. Hold two thoughts simultaneously, remain skeptical, demand rigorous proof, but also stay open to possibilities that seem far-fetched. Don't dismiss unusual claims simply because they're unusual, but don't accept them without evidence either. Walk that narrow path between closed-minded dismissal and credulous acceptance, because somewhere on that path, in that space of informed uncertainty, is where truth lives. And the truth about 3i Atlas, whatever it turns out to be, promises to be extraordinary. If you're ready to explore this mystery with intellectual honesty and emotional openness, if you want to understand what's really happening in the data and what it might mean for humanity, then hit that like button right now. Drop a comment telling me what you think could explain these bizarre ejections, natural phenomenon, or something more. Because this conversation is just beginning, and I want to know where you stand as we unpack one of the most intriguing cosmic mysteries of our time. Let's start by looking at exactly what makes 3i Atlas so scientifically baffling, and why conventional comet physics is failing to explain what observers are seeing. To understand why 3i Atlas has scientists scratching their heads, you first need to understand how comets normally behave. These are ancient objects, frozen remnants from the formation of planetary systems, composed mostly of ice, rock, and organic compounds. When a comet approaches a star, the increasing heat causes volatiles, frozen gases like water, carbon monoxide, and methane, to sublimate, transitioning directly from solid to gas without passing through a liquid phase. This outgassing creates the characteristic tail we associate with comets, that luminous streak that can stretch for millions of miles, always pointing away from the sun due to solar radiation pressure and the solar wind pushing the material outward. The physics is straightforward and predictable. As the sun heats a comet's surface unevenly, because the object is rotating and different areas receive different amounts of solar energy, jets form where pockets of volatile material suddenly release. These jets are chaotic, variable, and tied directly to the comet's rotation and the location of ice deposits beneath its surface. They're messy, unpredictable, and they follow patterns we can model using thermodynamics and fluid dynamics. We've observed thousands of comets over centuries, and while each one has unique characteristics, they all operate within this basic framework. They all make sense according to physics we understand thoroughly. 3I Atlas doesn't follow these rules. The jets observed coming from this object are perpendicular to its trajectory, sideways ejecta that doesn't align with the expected outgassing pattern from solar heating. Think about what that means. Normal comet jets are driven by the sun heating the surface, so they should primarily point away from the sun, propelled by the pressure of expanding gas. But 3I Atlas is ejecting material at right angles to the path you'd expect if solar heating were the driving force. It's like watching a car accelerate forward but seeing exhaust shoot out the sides instead of the back. Something about the mechanism doesn't match the expected cause. Then there's the linearity of these jets. Comet jets are typically broad, diffuse plumes that spread out as the material expands into space. They're not laser-straight beams, but the observations of 3I Atlas show remarkably linear streams, narrow channels of ejected material that maintain their structure over considerable distances. This is geometrically unusual, and suggests either a highly collimated ejection mechanism or solid objects travelling in ballistic trajectories rather than expanding gas clouds. When you see narrow, straight trajectories in space, you're usually looking at solid objects following Newtonian paths, not diffuse material being blown by pressure gradients. The X-shaped pattern is perhaps the most visually striking anomaly. After perihelion, the point of closest approach to the Sun, multiple observation sessions captured this distinctive cross-formation created by the ejection events. An X pattern implies symmetry, coordination, and timing that's hard to reconcile with random outgassing. Natural processes can occasionally create surprising symmetries. We see them in crystals and snowflakes, in various geological and physical phenomena, but they require very specific conditions. For a comet to spontaneously produce an X pattern through random volatile release requires a configuration of internal structure and composition that's not just unusual but borderline implausible. You'd need perfectly positioned volatile pockets releasing at precisely coordinated times, while the object rotates in exactly the right way to create that visual geometry. Possible, perhaps, likely. That's where doubt creeps in. Loeb presented these anomalies to the scientific community with characteristic boldness, laying out the observations and highlighting each aspect that deviates from standard comet behaviour. His analysis wasn't based on wild speculation but on careful examination of the imaging data and photometric measurements. He noted the persistence of the ejection events over multiple observation windows, indicating this wasn't a brief, explosive fragmentation, but an ongoing process unfolding over time. He emphasized the discrete nature of the ejected objects, not continuous streams of dust, but separate, distinct bodies being released in what appeared to be sequential events. Now, here's where scientific interpretation becomes both fascinating and contentious. The data itself is not in dispute. The images exist. The observations have been replicated by multiple independent sources. But what that data means, how we interpret it, that's where scientists diverge dramatically. Some see exotic but ultimately natural comet behaviour, perhaps indicative of unusual internal structure or composition we haven't encountered before. Others see something that strains natural explanations to the breaking point and requires considering alternatives we've traditionally dismissed as beyond the scope of serious scientific inquiry. The challenge with anomalies like this is that our explanatory frameworks are built on experience. And we understand comet physics so well because we've observed so many comets over such a long period. But that experience is limited to comets from our solar system, objects that formed under the specific conditions present in our particular protoplanetary disk. Interstellar comets come from different environments, different chemical compositions, different formation histories. Maybe interstellar comets from certain types of star systems naturally develop structures that produce these unusual ejection patterns. Maybe there's exotic ice chemistries or internal layering that we've never encountered that can explain this behavior. These are reasonable possibilities that deserve investigation, but there's a limit to how far you can stretch natural explanations before they become more contrived than the extraordinary alternatives they're meant to replace. If you have to invent entirely new comet physics, postulate unknown ice compositions, and assume improbable structural configurations all working together perfectly to produce the observed pattern, at what point does Occam's razor, the principle that simpler explanations are generally better, start favouring the extraordinary hypothesis? This is the razor's edge that scientists are walking right now with 3i Atlas. Part of the difficulty lies in the limitations of our observational capabilities. We're looking at a small, distant object with telescopes designed primarily for much larger celestial bodies. The resolution isn't enough to see fine surface details or directly measure the size and composition of the ejected objects. We're working with pixels, with brightness variations, with indirect inference rather than direct observation. It's like trying to diagnose a medical condition from a blurry photograph. You can see that something's wrong, but determining exactly what requires better imaging, more data, closer examination. This is where the scientific process reveals its true character. When faced with ambiguous data and competing hypotheses, science doesn't rush to conclusions. It demands more evidence. It sets up tests that can distinguish between alternatives. It makes predictions based on different explanatory frameworks, and then checks those predictions against new observations. This is happening right now with 3i Atlas. Observatories are scheduling follow-up observations, trying to catch the next ejection event, hoping to gather spectroscopic data that might reveal the composition of the ejected material, tracking the object's trajectory to see if the ejections are affecting its orbit in detectable ways. Each piece of new data will either support one interpretation or another, gradually narrowing the range of plausible explanations until we converge on something approaching truth. But we're early in that process. The anomalies have been identified. The competing hypotheses have been proposed. Now comes the slow, painstaking work of testing, analysing, debating, and refining our understanding based on accumulating evidence. It's not a process that yields instant answers, and in our age of immediate information, that patience can feel frustrating. We want to know now. We want certainty. But the universe doesn't owe us convenient, quick answers. What makes this particular anomaly so captivating is its position at the intersection of multiple profound questions. It's not just about understanding comet physics or interstellar object composition. It's about the possibility of contact, of encountering evidence of other technological civilizations, of fundamentally recontextualizing humanity's place in the cosmic order. Those stakes raise the emotional temperature of the debate, make people more invested in particular interpretations, and create a dynamic where scientific objectivity has to constantly battle against psychological biases and deeply held beliefs about what we want to be true. The scientists watching 3i Atlas right now are navigating this complex terrain, trying to maintain intellectual rigor while acknowledging that genuinely extraordinary phenomena occasionally do occur and deserve serious consideration. They're balancing skepticism with openness, caution with curiosity, established knowledge with the humility to admit that our understanding is incomplete. And in that balance, in that tension between what we know and what we're observing, lies the cutting edge of discovery, the place where science advances, where paradigms shift, where our species occasionally glimpses truths that expand our conception of reality itself. With the anomalies clearly laid out and the scientific puzzle defined, we need to examine the conventional explanations being proposed, the natural mechanisms that could potentially account for what we're seeing without requiring us to invoke anything extraordinary. Science has a deeply ingrained instinct for parsimony. Before considering exotic explanations, before entertaining possibilities that require overturning established understanding, scientists systematically work through prosaic alternatives using known physics, observed phenomena, and well-tested theoretical frameworks. This isn't closed-mindedness, it's intellectual discipline. Extraordinary claims require extraordinary evidence precisely because extraordinary explanations carry a much higher burden of proof than mundane ones. So when faced with 3i Atlas and its strange behaviour, the mainstream scientific community's first response is to ask what natural processes could create these observations. tidal forces represent one of the most straightforward explanations for fragmentation and ejection events. As a comet approaches the Sun, it experiences gravitational stress. The side facing the Sun feels stronger gravitational pull than the far side, creating a differential force that tries to stretch the object. If a comet has structural weaknesses, cracks, fissures, regions of varying density, these tidal forces can tear it apart. We've observed comets fragmenting during solar approach many times. The fragments then follow separate trajectories, creating multiple objects where there was once one. Could this explain the mini probes? Could we be watching tidal fragmentation in real time, with pieces breaking off and following ballistic paths that happen, to create geometric patterns from our viewing angle? It's possible, but there are problems. Tidal fragmentation typically happens at perihelion or shortly after, when the gravitational stress is greatest. It's usually sudden and catastrophic, not a drawn-out process releasing objects in seemingly regular intervals, and the resulting fragments don't normally maintain such linear trajectories or create symmetrical patterns. They scatter more chaotically as each piece responds to slightly different forces and has different structural properties. The timing and geometry of 3I Atlas's ejections don't quite match the profile of typical tidal disruption. Then there's the possibility of exotic volatile compositions creating unusual outgassing behavior. Perhaps 3I Atlas contains ice types we haven't encountered before, clathrates with unusual thermal properties, frozen gases that sublimate under specific conditions found only in interstellar environments, or layered structures that create directed jets when heated. If the internal composition is sufficiently unusual, maybe it could produce the observed linear jets and regular ejection timing through purely natural thermodynamic processes. This hypothesis has the advantage of not requiring us to abandon comet physics entirely, just to expand it to encompass compositions and structures we haven't previously studied. But again, there are difficulties. While we can propose unusual compositions in theory, we need mechanisms that explain not just one anomaly, but all of them simultaneously. The sideways jets, the linearity, the X-pattern, the discrete objects, the timing, each needs to emerge naturally from this exotic composition hypothesis, and as you stack requirements, the explanation becomes increasingly contrived. You're essentially designing a bespoke comet with precisely calibrated properties to match observations, which starts to feel like reverse engineering rather than predicting from first principles. Radiation pressure offers another avenue of explanation. Solar radiation can exert force on small particles, pushing them and altering their trajectories. If 3I Atlas is shedding dust or small fragments, radiation pressure could potentially shape their paths in ways that create unexpected patterns. Combined with the object's rotation and the geometry of solar illumination, maybe this could produce the observed effects. Some scientists have proposed sophisticated models incorporating these factors, attempting to show that the right combination of rotation rate, ejection velocities, particle sizes, and radiation pressure could yield something resembling what we're seeing. These models are mathematically elegant and physically plausible in isolation. The problem is validation. Do the parameters required by these models match what we can independently measure about 3I Atlas? Does the object's rotation period align with what the model needs? Are the ejection velocities within the range that natural outgassing could produce? Are the particle sizes consistent with what spectroscopy suggests? As scientists work through these checks, they're finding that while you can construct models that work mathematically, constraining them with actual observational data makes them increasingly uncomfortable. You can make them fit, but it requires fine-tuning that feels suspiciously ad hoc. The scientific community's skepticism toward the artificial hypothesis isn't rooted in dogmatic rejection of the possibility of extraterrestrial intelligence. Most astronomers would be thrilled to discover genuine evidence of other civilizations. It would be the discovery of a lifetime, a career-defining moment that would reshape humanity's understanding of its cosmic context. The skepticism comes from experience with false alarms, with initial observations that seemed extraordinary, but turned out to have prosaic explanations once better data came in. The history of astronomy is littered with such episodes. Pulsars initially thought to be alien beacons, signals that seemed artificial but were actually natural astrophysical phenomena, patterns that appeared designed but emerged from coincidence and selective attention. This history creates a kind of professional wariness, a learned caution, about jumping to extraordinary conclusions based on limited data. Scientists have been burned before by premature announcements that later had to be walked back embarrassingly. That creates institutional pressure to exhaust natural explanations before even considering alternatives to maintain a conservative stance that protects reputations and preserves credibility. This conservatism serves science well in many contexts. It prevents the field from being derailed by every anomaly, maintains high evidentiary standards, and preserves public trust by ensuring that announced discoveries are robust and replicable. But conservatism can also become a blind spot. If you're so committed to finding natural explanations that you unconsciously twist evidence to fit preferred interpretations, you risk missing genuinely novel phenomena. If the default assumption is always that anomalies must have prosaic explanations, you might fail to recognize the rare instances when something genuinely extraordinary is occurring. Science needs skepticism, but it also needs openness, the flexibility to recognize when accumulated evidence is pointing toward conclusions that challenge established frameworks. The debate around 3i Atlas is partly a debate about where that balance should lie. Some scientists are saying we haven't exhausted natural explanations yet, that there are still models to test and observations to gather before we need to consider exotic alternatives. Others, like Avi Loeb, are arguing that the natural explanations being proposed are themselves becoming so exotic and contrived that it's intellectually dishonest to pretend they're more parsimonious than the artificial hypothesis. Both sides have legitimate points, and the tension between them is actually healthy for the scientific process. It ensures that all possibilities get rigorous examination, that assumptions get challenged, and that conclusions emerge from debate rather than consensus driven by groupthink. What's crucial to understand is that this isn't a binary choice between accepting or rejecting an alien explanation. Science doesn't work that way. Instead, there's a continuum of plausibility, a constantly updated probability assessment that shifts as new evidence comes in. Right now, most scientists would place artificial origin at very low probability. Not zero, but low enough that it shouldn't be the working hypothesis. Natural explanations, even exotic ones, sit at higher probability because they require fewer extraordinary assumptions. But probabilities can shift. If new observations continue to defy natural explanations, if the anomalies persist and multiply rather than resolving with better data, those probability estimates will change. The artificial hypothesis will move from fringe to worth serious consideration to potential explanation, tracking the evidence. This is the scientific method in action, messy and contentious, but ultimately self-correcting. Hypotheses compete, data accumulates, models get refined or discarded. Consensus gradually emerges not through authority or voting, but through the weight of evidence becoming so overwhelming that dissent becomes untenable. We're nowhere near that point with 3i Atlas. The evidence is intriguing but ambiguous. The observations are real but subject to multiple interpretations. We're in that uncomfortable early stage where mystery exceeds understanding, where speculation fills gaps that data will eventually close. The scientists urging caution aren't enemies of discovery. They're guardians of intellectual rigor, insisting that we follow evidence rather than wishes, that we maintain standards that have served science well for centuries. But the scientists asking uncomfortable questions aren't crackpots either. They're performing the equally essential role of ensuring we don't dismiss possibilities simply because they're unfamiliar or challenging. Both perspectives are necessary. Both contribute to the eventual emergence of truth, and both are currently focused intensely on 3i Atlas, watching its every move, analysing its every ejection, hoping that continued observation will tip the scales decisively toward one interpretation or another. With the skeptical case clearly laid out, let's turn to the controversial hypothesis that's captured public imagination and sparked intense debate. Avi Loeb's suggestion that we might be watching alien technology in action. Avi Loeb is not a fringe figure. He's chaired Harvard's astronomy department, published hundreds of peer-reviewed papers, mentored dozens of graduate students, and contributed significantly to mainstream astrophysics across multiple subfields. His credentials are impeccable, his technical expertise unquestionable, yet he's become a controversial figure in astronomy, not because his science is sloppy, but because he's willing to publicly entertain hypotheses that many of his colleagues consider beyond the pale of serious scientific discourse. He asks questions that make people uncomfortable. He proposes interpretations that challenge professional norms, and with 3i Atlas, he's once again stepping into that uncomfortable space where rigorous analysis meets speculative possibility. Loeb's hypothesis is straightforward in concept, though profound in implication. He suggests that 3i Atlas might be an artificial object, either entirely constructed or a natural body that's been modified to carry technological payloads. The mini-probes being released, according to this interpretation, could be reconnaissance devices designed to gather data about our solar system, small autonomous instruments deployed to survey stellar environments the parent craft passes through. This would explain the organized nature of the releases, the linear trajectories suggesting deliberate propulsion, or ejection, rather than random fragmentation, and the geometric patterns that emerge when plotting the ejection events over time. The reasoning behind this hypothesis starts with elimination. If natural processes struggle to explain the observations, and if the natural explanations being proposed require increasingly exotic and unlikely conditions, then at some point you have to ask whether a different category of explanation might actually be simpler. An artificial object deploying probes would naturally exhibit precisely the characteristics we're observing: controlled ejections, geometric patterns, sustained activity over time, discrete objects following ballistic trajectories. You wouldn't need to postulate unknown ice chemistries or improbable internal structures. The observations would follow directly and obviously from the artificial hypothesis without requiring any special pleading or parameter fine-tuning. This is where Loeb invokes Occam's razor differently than his critics. They say the natural explanation is simpler because it doesn't require assuming the existence of alien civilizations. He says the artificial explanation is simpler because it doesn't require inventing new physics or contriving unlikely natural configurations. It's a philosophical dispute about what counts as a simpler explanation: fewer ontological commitments or fewer ad hoc assumptions. Both perspectives have merit, and the disagreement reflects deeper questions about how we evaluate competing scientific hypotheses when facing genuinely novel phenomena. Loeb also places 3i Atlas in a broader context of interstellar object observations. He notes that Oumuamua, the first confirmed interstellar visitor, also exhibited anomalies, most notably unexpected acceleration that couldn't be fully explained by outgassing or gravitational forces alone. That anomaly sparked similar debates, with Loeb proposing artificial origins and most scientists offering increasingly complex natural explanations. Now we have 3i Atlas presenting a different set of anomalies but following a similar pattern. Initial observations that seem strange, growing difficulty in crafting satisfying natural explanations, and a scientific community deeply reluctant to consider artificial alternatives, no matter how well they might fit the data. From Loeb's perspective, this reluctance reflects cognitive bias rather than scientific rigor. He argues that astronomy has developed a kind of cultural taboo around the search for extraterrestrial intelligence, treating it as less legitimate than other research areas despite its profound importance. This taboo makes scientists unconsciously avoid interpretations that invoke intelligence or technology, preferring even highly contrived natural explanations to straightforward artificial ones. He sees this bias as limiting our ability to recognize potentially revolutionary discoveries, blinding us to possibilities that should at least be seriously considered alongside conventional alternatives. The probe hypothesis itself has technical substance beyond the philosophical arguments. If 3i Atlas is deploying reconnaissance devices, what would we expect to observe? The probes would need to be ejected with sufficient velocity to separate from the parent body, but not so fast that they escape the solar system entirely before completing their mission. They'd likely be small, large enough to carry instrumentation, but small enough to be practical to transport across interstellar distances. They'd follow ballistic trajectories once released, potentially making small course corrections using minimal propulsion, and they'd be deployed in patterns that maximize coverage or target specific regions of interest, perhaps the inner solar system where planetary activity is concentrated, or trajectories that pass near Earth and other potentially inhabited worlds. Remarkably, the observations of 3i Atlas could be consistent with exactly these expectations. The ejection velocities appear to be in the right range to place the released objects into solar orbits rather than escape trajectories. The objects are indeed small, at the limits of detectability, which is what you'd expect for miniaturized probes. The trajectories, while needing more observation to fully characterize, don't appear to be purely passive, but might show subtle signs of guidance or attitude control, and the timing of releases correlates with 3i Atlas's position and trajectory in ways that could reflect strategic deployment based on optimal survey positions. None of this constitutes proof. All of it remains circumstantial and subject to alternative interpretations. But it's also not baseless speculation. Loeb is working from actual observational data, applying rigorous analysis and proposing hypotheses that make testable predictions. His approach is scientifically legitimate even if his conclusions are controversial. And that's an important distinction. You can disagree with his interpretation without dismissing his methodology or questioning his scientific credentials. The challenge with the artificial hypothesis is that it carries enormous implications that extend far beyond astronomy. If 3i Atlas really is releasing alien probes, it means we're not alone. It means technological civilization exists elsewhere, has existed long enough to develop interstellar travel capabilities, and is actively exploring the galaxy. It means we're living in a cosmos populated by other minds, other societies, other forms of intelligence that have reached similar or greater levels of technological sophistication. Those implications are so profound, so transformative of our cosmic worldview that they demand extraordinary evidence. Accepting them casually would be intellectually irresponsible, but rejecting them reflexively, refusing to seriously consider them even when evidence points in that direction, would be equally irresponsible. Loeb's contribution isn't necessarily proving that 3i Atlas is artificial. It may well turn out to have a natural explanation once we gather more data. His contribution is forcing the scientific community to articulate exactly what evidence would be sufficient to conclude something is artificial, and to honestly examine whether professional biases are causing us to set that evidentiary bar unreasonably high. He's challenging astronomy to live up to its stated commitment to follow evidence wherever it leads, even, especially, when it leads to uncomfortable conclusions that challenge our assumptions about humanity's cosmic uniqueness. This challenge has sparked intense pushback, not just because colleagues disagree with his interpretation, but because he's touching a nerve about how science actually operates versus how it claims to operate. The ideal of science is pure objectivity, following data to conclusions without bias or preconception. The reality is that scientists are human, embedded in professional cultures with unstated norms and career incentives that shape what questions get asked, what hypotheses get taken seriously, and what conclusions can be safely advocated without professional penalty. Loeb is exposing that gap, and institutions don't like having their unstated assumptions made explicit and questioned. Whether you agree with his interpretation of 3i Atlas or not, you have to admire the intellectual courage it takes to stake out controversial positions in the face of professional disapproval. Science advances partly through consensus and incremental progress, but also through mavericks willing to question orthodoxy and explore ideas that mainstream thinking has prematurely dismissed. History is full of such figures, scientists who were ridiculed in their time but vindicated later when evidence accumulated in favour of their heterodox views. History is also full of cranks who were wrong and stayed wrong. The challenge is distinguishing between the two categories before history renders its verdict, and that's genuinely difficult when you're living through the controversy rather than looking back with hindsight. What matters now is not choosing sides in this debate, but watching how it unfolds. Will new observations clarify the situation, providing data that clearly favours natural or artificial interpretations? Will someone propose a natural mechanism that elegantly explains all the anomalies without contrivance? Or will the artificial hypothesis gain credibility as attempts to explain the observations naturally continue to fall short? These questions will be answered by observation, analysis, and time. And in the meantime, we're privileged to witness this process unfold in real time, to see science grappling with genuine mystery in an age where most discoveries feel incremental rather than revolutionary. The hypothesis is on the table, controversial but serious. Now let's examine the actual evidence being gathered, the observations that fuel this entire debate, and that will ultimately determine which interpretation prevails. Evidence matters more than speculation, and with 3i Atlas we have actual data to work with, not just theoretical possibilities. The observations began in earnest after the object's perihelion passage, when it was closest to the Sun and most active. Multiple observatories tracked it, capturing images across different wavelengths and with varying levels of resolution. What those images revealed immediately caught attention. This wasn't standard comet behaviour. The visual data showed distinct asymmetries, linear features in the ejector, and patterns that persisted across multiple observation sessions separated by days and weeks. The key evidence comes from photometric analysis, measuring how the brightness of 3i Atlas changes over time. When objects are ejected from a comet, they temporarily increase the overall brightness as newly exposed material reflects sunlight and as the ejected particles scatter light in all directions. By carefully monitoring these brightness changes, astronomers can infer when ejection events occur, roughly how much material is involved, and something about the geometry of the ejections. For 3i Atlas, this analysis revealed episodic brightening events, sudden increases in luminosity that then gradually faded, occurring in a temporal pattern that suggested discrete ejection episodes rather than continuous outgassing. The imaging data provided visual confirmation of what the photometry suggested. Time series photographs showed material streaming away from the nucleus in directions that didn't align with the expected dust-tail orientation. The streams were narrow and maintained their structure over surprisingly large distances, characteristics more consistent with solid objects in ballistic flight than with expanding gas clouds. And crucially, these features persisted. They weren't transient artifacts of a single observation, but repeatable phenomena that multiple independent observers confirmed using different instruments and techniques. Spectroscopic data added another layer of information. By analysing the light reflected or emitted by 3i Atlas and its ejector, astronomers can determine composition, what elements and molecules are present. The spectra showed some expected comet signatures, water ice, carbon-based molecules, silicate dust, but also some puzzling features that didn't match typical comet compositions perfectly. There were hints of materials or temperature regimes that seemed unusual, though interpreting spectra is complex and subject to uncertainties about observing geometry, illumination conditions, and the mixing of materials with different spectral properties. The timeline of events matters significantly. The ejections didn't happen randomly, but appeared to correlate with the object's orbital position and its rotation. If you map out when ejection events occurred and where 3i Atlas was in its orbit at those times, patterns emerge that could indicate either solar heating triggering outbursts at specific locations on the nucleus, or, alternatively, predetermined deployment schedules if the artificial hypothesis is correct. Distinguishing between these interpretations requires precise timing data and detailed modelling of both thermal processes and possible deliberate scheduling, work that's ongoing as more observations accumulate. Expert reactions have been predictably mixed. Some astronomers look at this data and see unusual but ultimately explicable natural phenomena. They focus on the aspects that do fit comet models, acknowledge the anomalies, but express confidence that refined understanding of interstellar object composition and structure will eventually provide satisfying explanations. These scientists emphasize the preliminary nature of current data, noting that definitive conclusions require observations across longer time periods with higher resolution instruments than are currently being used. Others are less confident in natural explanations and more open to exotic alternatives. They point out that with each new observation, the anomalies are becoming more apparent rather than resolving into familiar patterns. They note the consistency of the unusual features across independent datasets, which argues against observational artifacts or misinterpretation. And they stress that remaining agnostic about extraordinary possibilities is not the same as advocating for them. You can acknowledge that current data doesn't fit conventional models without claiming to know what the correct interpretation is. NASA's official position has been characteristically cautious. Institutional statements emphasize the need for continued observation, avoiding premature conclusions while acknowledging that 3i Atlas presents interesting scientific questions worthy of dedicated study. This careful language reflects NASA's need to maintain public credibility. They can't be seen as either dismissing potentially significant discoveries or endorsing speculative interpretations without sufficient evidence. The agency has allocated telescope time for follow-up observations and encouraged coordination among research groups, signaling that they take the anomalies seriously, even while officially withholding judgment on interpretation. International observatory networks have joined the effort, recognizing that 3i Atlas offers a rare opportunity to study an active interstellar object in detail. These coordinated campaigns aim to catch the object during predicted outburst events, gathering simultaneous observations across multiple wavelengths and from different viewing angles to construct a three-dimensional picture of what's happening. The logistics are challenging. Telescope time is precious. Windows of optimal observability are limited by the object's brightness and position in the sky, and weather can derail carefully planned observation sessions. What's emerging from this collective effort is a dataset of unprecedented quality for an interstellar object. We've never had this much detailed information about the active behavior of something that originated beyond our solar system. Even if 3i Atlas ultimately proves to have a mundane explanation, the observations will significantly advance our understanding of interstellar object properties and behaviors. Science often works this way. Anomalies drive intensive study, and even when the extraordinary interpretation doesn't pan out, the investigation yields valuable knowledge that wouldn't have been gained without the initial mystery motivating the effort. The data also reveals limitations in our current capabilities. The size of the ejected objects, for instance, is at or below the resolution limits of available telescopes. We can see that discrete bodies are being released, but we can't directly image them individually or measure their sizes and shapes precisely. We're left inferring these properties from indirect measurements, which introduces uncertainty and allows for multiple interpretations of the same observations. Better data would help resolve the controversy, but getting that data requires technological capabilities we're only beginning to develop. This is where space-based observations become crucial. Ground-based telescopes, no matter how large or sophisticated, face limitations from atmospheric distortion, weather, and the filter effects of Earth's atmosphere on certain wavelengths. Space telescopes like Hubble or James Webb operate above these limitations, achieving resolutions and sensitivities that ground-based instruments can't match. Proposals are circulating to target 3i Atlas with these premier facilities, dedicating precious observing time to capture the highest quality data possible. Such observations could be definitive, either confirming the unusual nature of the ejections or revealing prosaic explanations that lower resolution data obscured. Amateur astronomers are also contributing, demonstrating that significant science doesn't always require billion-dollar facilities. Coordinated networks of skilled amateurs with modest but capable equipment have been tracking 3i Atlas, providing valuable long-term monitoring that captures variability and transient events that professional observations might miss due to their scheduled, intermittent nature. This crowdsourced astronomy is becoming increasingly important, filling gaps in professional coverage and occasionally making discoveries that redirect the attention of larger telescopes. The cumulative picture from all these observations is one of an object that's behaviorally distinct from standard comets, in ways that remain inadequately explained. The longer this situation persists, the more observation sessions that confirm rather than resolve the anomalies, the more pressure builds on conventional explanations, and the more seriously exotic alternatives must be considered. We're approaching a potential inflection point where accumulated evidence could tip interpretation decisively, one direction or another, transforming this from a minor scientific curiosity into either a major confirmation of known physics under unusual conditions or a genuine paradigm-challenging discovery. For now, the data supports saying that 3i Atlas is scientifically interesting, observationally anomalous, and deserving of continued intensive study. Whether it represents natural processes we don't fully understand or something more extraordinary remains an open question, one that only further observation and rigorous analysis will answer, and that's exactly where science should be at this stage, maintaining intellectual humility about the limits of current understanding, while systematically gathering the evidence needed to reach justified conclusions. With the evidence laid out and expert perspectives considered, let's turn to the most profound question this mystery raises. What would it actually mean if the extraordinary interpretation proves correct? Imagine for a moment that continued observation confirms the extraordinary hypothesis. Imagine that accumulated evidence becomes so compelling that even skeptical scientists have to acknowledge that 3i Atlas appears to be artificial, that those mini probes really are technological devices from an alien civilization. What happens next? Not just scientifically, but psychologically, culturally, philosophically. What would it mean for humanity to confirm with certainty that we're not alone in the universe, that we share the cosmos with other minds capable of thought, technology, and exploration? The immediate scientific impact would be revolutionary. Confirmation of extraterrestrial intelligence would instantly become the most important discovery in human history, overshadowing everything else in comparative significance. Every major scientific institution, would pivot resources toward understanding this finding, extracting every possible piece of information from the observations. We'd want to know everything. Where did the parent craft originate? How long has it been travelling? What's the technology powering it? What information are the probes gathering? How common are such missions in the galaxy? The questions would multiply faster than we could answer them, opening entirely new fields of study practically overnight. But beyond the immediate scientific excitement lies a deeper transformation of human self-understanding. For our entire history, we've existed in cosmic isolation, looking at the stars and wondering if anyone looks back. That wondering has shaped religions, philosophies, artistic expressions, and scientific inquiry across cultures and centuries. The loneliness of being apparently alone in a vast universe has been a fundamental condition of human existence. Confirmation of other intelligence shatters that condition permanently. We transition from wondering to knowing, from solitude to awareness of companionship, even if that companionship is distant and silent. Consider the psychological implications of this shift. Humanity would have to integrate into its collective consciousness the reality of existing in a populated galaxy, of being one civilization among potentially many, of not being the universe's only experiment in conscious technological development. For some, this would be exhilarating. Confirmation that the universe is rich with life and mind, that the cosmic story is vastly more interesting than a dead expanse of lifeless matter. For others, it might be destabilizing, challenging religious beliefs about humanity's special creation, raising anxieties about our place in a cosmic hierarchy of civilizations, generating fears about contact and its consequences. The diversity of human reactions would be enormous. Different cultures, different belief systems, different philosophical traditions would interpret this discovery through their particular lenses, finding different meanings and drawing different conclusions. Some would see it as confirmation of existing beliefs about cosmic plurality. Others would struggle to reconcile it with foundational assumptions about human uniqueness. There would be excitement and fear, wonder and anxiety, hope and dread, all swirling together in a global conversation about what this means and what we should do in response. Practically, we'd face immediate questions about communication and response. Should we attempt to signal the probes to indicate that we're aware of them and interested in contact? Or would that be dangerous, potentially drawing unwanted attention from civilizations whose intentions and capabilities we can't assess? The debate between those advocating caution and those advocating bold outreach would intensify dramatically, with stakes that feel existentially significant. This isn't abstract anymore. It's a real decision about how humanity presents itself to cosmic neighbours we've just confirmed exist. The technology question would fascinate and tantalize us. If a civilization can build probes and send them on interstellar journeys that last thousands or millions of years, what else can they do? What does their homeworld look like? What's their history, their culture, their science? We'd be staring at evidence of capabilities far beyond our current level, which would be humbling and inspiring simultaneously. It would concretely demonstrate that the technological challenges we face, energy, propulsion, longevity of systems, autonomous operation, are solvable, that civilizations can achieve interstellar presence if they survive and develop long enough. This leads to perhaps the most profound implication, the perspective on humanity's own future. Confirmation that technological civilization exists elsewhere and has achieved interstellar capability would be powerful evidence that the so-called Great Filter, the proposed explanation for why we don't see obvious signs of alien civilizations despite the apparent likelihood of their existence, lies behind us rather than ahead. It would suggest that civilizations can survive their technological adolescence, can navigate the dangers of advanced technology without destroying themselves, can persist long enough to become spacefaring and explore beyond their home systems. That would be profoundly hopeful for our own prospects, suggesting that our current challenges, environmental, political, technological, are surmountable with wisdom and effort. But there's also a darker possibility that this scenario raises. If interstellar probes are present in our solar system, how many civilizations have sent them? How long have they been coming? Are we being observed by multiple alien intelligences? Are development monitored by entities with purposes and ethics we can't fathom? That shifts the emotional tone from lonely but special to observed and assessed, which carries its own anxieties. We'd wonder what they think of us, whether they judge our conflicts and failures, whether they're waiting for us to reach some developmental threshold before making themselves known, or whether they have no interest in contact regardless of our development level. The theological implications deserve serious consideration. Every major religion would have to grapple with how extraterrestrial intelligence fits into its cosmology and doctrine. Some religious traditions have already developed frameworks for this possibility, but others would face genuine challenges. Questions about salvation, divine creation, the uniqueness of human spiritual experience. These would all need re-examination in light of confirmed cosmic plurality. For many believers, this might enrich rather than challenge faith, but the transition would still require profound theological work. Philosophically, we'd face questions about intelligence, consciousness, and what it means to be a mind in the universe. Meeting or confirming another intelligence, even indirectly through their technology, would give us comparison points we've never had. Are all technological civilizations similar in their developmental arcs? Do they face the same ethical questions? Do they develop similar sciences and mathematics, or are there fundamentally different approaches to understanding reality that alien minds might employ? These questions move from pure speculation to potentially answerable queries once we know with certainty that other examples exist. The societal impacts would ripple through every domain. Education would need to incorporate this reality. Children would grow up in a world where cosmic plurality is established fact rather than speculation. Science fiction would shift from exploring the possibility of contact to exploring its consequences, with the speculative element moving from do they exist to what are they like. Space exploration would gain renewed urgency and purpose, with the search for life and intelligence moving from abstract scientific interest to concrete investigation of a confirmed phenomenon. Economically and politically, the impacts are harder to predict but potentially significant. Would nations cooperate more, recognizing that humanity faces cosmic context bigger than terrestrial conflicts? Or would competition intensify as different countries and blocs race to understand alien technology and potentially gain strategic advantages? Would the confirmed existence of advanced civilizations make our own conflicts seem petty and motivate greater cooperation? Or would it generate new forms of competition and anxiety? History suggests both impulses would be present, with the outcome depending on leadership, wisdom, and chance. There's also the question of timescale and patience. If 3i Atlas is confirmed as artificial, we likely won't get immediate answers to our burning questions. The probes aren't going to start broadcasting explanations or slowing down for tea and conversation. We'd be left with indirect evidence, inferences from observations, and the frustrating awareness that the beings who created this technology are light years away, perhaps long dead if the mission launched eons ago. We'd have confirmation without communication, knowledge of existence without relationship. That's its own kind of challenge, having the most important question answered while all the follow-up questions remain stubbornly unresolved. Yet even this limited confirmation would transform us. We'd know the universe is alive with intelligence. We'd know technological civilization is achievable and can persist across cosmic timescales. We'd know we're not alone in the endeavor of understanding reality, creating meaning, exploring the possible. Those knowings would reshape human consciousness in ways both subtle and profound, filtering into art, literature, science, philosophy, religion, and daily life. Future generations would look back on this discovery as a hinge point in history, a before and after moment when humanity's cosmic story fundamentally changed direction. This is what's at stake in the question of 3i Atlas's nature. It's not just an academic puzzle for astronomers to solve, it's a question that touches the deepest layers of human identity, purpose, and possibility. And that's precisely why the scientific community is both fascinated and cautious, excited and wary, eager for answers yet insistent on rigorous standards. The implications are too vast to get wrong, too important to rush, too profound to treat carelessly. So the investigation continues methodically, patiently, with the full awareness that whatever the answer turns out to be, it will matter immensely. With those weighty implications in mind, let's turn to the practical question of what happens next, how we'll continue investigating this mystery, and what opportunities lie ahead for advancing our understanding. The investigation of 3i Atlas is far from over. In fact, we're still in the early stages of understanding this object, and numerous opportunities lie ahead to gather more data, test competing hypotheses, and hopefully converge on definitive answers about its nature. The trajectory of 3i Atlas through our solar system is well characterized now, which means astronomers can predict optimal observation windows and plan coordinated campaigns to maximize the scientific return from this rare interstellar visitor. The most immediate opportunity involves continued photometric monitoring as the object moves away from the Sun. If the ejection events persist, tracking their frequency and characteristics as solar heating decreases will provide crucial information about what's driving them. Natural outgassing should decline predictably as the comet gets farther from the Sun and colder, following well-understood thermal models. If the ejections continue at similar rates or show patterns that don't correlate with solar distance, that would be a significant data point favouring non-thermal explanations. Every observation session over the coming months adds pieces to this puzzle, gradually revealing whether the activity is primarily solar-driven or operating on some other principle. Spectroscopic follow-up represents another critical avenue. The initial spectra captured intriguing but ambiguous features that need confirmation and deeper analysis. More detailed spectroscopy, particularly of the ejected material itself rather than just the nucleus, could reveal composition with much greater precision. If the mini-probes are natural fragments, their spectra should match the parent body and look like typical comet material. If they're something else, manufactured objects with different compositions, that should eventually show up in spectroscopic signatures that don't match natural expectations. Getting clean spectra requires good observing conditions and sufficient brightness, which depends on the object's distance and activity level, making timing crucial. High-resolution imaging from premier facilities offers perhaps the most exciting prospect. Proposals are being prepared to target 3i Atlas with the Hubble Space Telescope and possibly the James Webb Space Telescope, instruments with resolving power far exceeding what's been used so far. These observations could potentially image the ejected objects directly, rather than just inferring their presence from brightness variations and morphology. Direct imaging would allow size estimates, might reveal shapes or surface properties, and would provide the clearest evidence yet about whether we're looking at irregular natural fragments or something more structured. The competition for time on these oversubscribed telescopes is fierce, but the scientific importance of 3i Atlas makes a compelling case for observation. Ground-based interferometry is another technique that could contribute valuable data. By combining light from multiple telescopes separated by large distances, astronomers can achieve resolution comparable to a telescope with an aperture as large as the separation between the instruments. This technique is challenging and requires careful coordination, but it's been successfully used for studying other small solar system bodies. Applied to 3i Atlas, interferometry might reveal details about the nuclear structure and the geometry of the ejection process that single telescope observations can't capture. Radar observations offer a completely different approach. Bouncing radio waves off solar system objects and analysing the return signal can provide information about size, shape, rotation, and surface properties with remarkable precision. The technique has been used successfully on asteroids and comets within our solar system. The challenge with 3i Atlas is distance. Radar signal strength falls off rapidly, making detection increasingly difficult as the object moves away from Earth. But if observations can be scheduled during a close approach to our planet, radar might provide unique data unavailable through any other technique, particularly about the physical properties and rotation state of the nucleus. Citizen science plays an increasingly important role in astronomical research, and 3i Atlas presents excellent opportunities for amateur contributions. Networks of amateur astronomers with moderate-sized telescopes can provide continuous monitoring that professional facilities can't match due to their scheduled, intermittent observation patterns. Amateurs have detected transient brightening events, documented activity variations, and contributed timing data that fills crucial gaps in the professional observation timeline. As interest in 3i Atlas grows, more amateurs will likely participate, creating a distributed observation network that collectively rivals professional capabilities. The organizational challenge involves coordinating all these efforts. Professional observers with different telescopes, amateur networks, theorists developing models, spectroscopists analyzing composition data, dynamicists tracking orbital evolution. International collaboration is essential, sharing data rapidly and openly so that insights from one observation can inform planning for the next. This kind of coordinated campaign has become increasingly common in astronomy, facilitated by modern communication technology and a culture of open data sharing that's developed over recent decades. Future opportunities might also involve spacecraft missions, though these would be long-term prospects given the planning and development time required. If 3i Atlas proves sufficiently interesting and accessible, proposals could emerge for dedicated missions to fly by or even intercept the object, gathering data at close range that no Earth-based telescope can match. Such missions would be expensive and technically challenging, requiring propulsion systems capable of matching velocities with an object on a hyperbolic solar system trajectory. But the scientific payoff could be enormous. We'd potentially get direct imaging, in situ composition measurements, close-up examination of ejection sites, and possibly even sample return if the mission is designed ambitiously enough. The timeline for these various observations and missions varies dramatically. Continued ground-based monitoring is happening now and will continue as long as the object remains bright enough to observe. Space telescope observations might happen within months if proposals are approved. Interferometry campaigns could be organised on similar timescales, but dedicated spacecraft missions, if pursued at all, would be years or decades in development. So we're looking at a multi-year investigation with rolling results, where understanding builds incrementally as each new observation adds detail and constrains interpretation. Communication of results to the public represents another important consideration. The controversy around 3i Atlas has generated significant public interest, with media coverage and social media discussion amplifying both the excitement and the speculation. Scientists face the challenge of sharing findings as they emerge without overstating certainty or encouraging premature conclusions. This requires careful language, acknowledging what's known and unknown, explaining the process of scientific investigation rather than just announcing results. Done well, this public engagement can build scientific literacy and help people understand how science actually works. Messy, iterative, uncertain, gradually converging on truth through accumulated evidence. Educational opportunities abound as well. 3i Atlas provides a real-time case study in the scientific method, showing how hypotheses are tested, how data constrains interpretation, how scientists navigate uncertainty and debate. Teachers can use this ongoing investigation in classrooms, helping students understand that science isn't just a body of facts but an active process of inquiry. The controversy itself, the tension between mainstream and heterodox interpretations, offers valuable lessons about how scientific consensus emerges and why skepticism is important, even as we remain open to surprising discoveries. The role of funding in all this shouldn't be underestimated. Telescope time costs money. Data analysis requires researchers with salaries. Spacecraft missions need budgets in the hundreds of millions or billions of dollars. Scientific investigation at this level depends on institutional support, grant funding, and ultimately public and governmental willingness to invest in basic research, without guaranteed practical payoff. The case for this investment rests on the intrinsic value of knowledge, the long-term benefits of scientific advancement, and the inspiration that discovery provides. 3i Atlas, regardless of its ultimate explanation, demonstrates why that investment matters. We're answering fundamental questions about our cosmic environment, expanding human understanding, and potentially making discoveries that reshape our worldview. As observations continue and data accumulates, the scientific community will periodically assess the state of knowledge and update interpretations accordingly. This isn't a linear process where each observation clearly favours one hypothesis over others. Sometimes new data raises more questions than it answers, complicates rather than clarifies, opens new interpretive possibilities that nobody had previously considered. That's normal in science, especially when studying genuinely novel phenomena. The key is maintaining intellectual honesty, following evidence rather than preferences, and accepting that definitive answers sometimes take longer than we'd like. For those of us watching this unfold, there's something thrilling about witnessing science in action at the frontier of discovery. We're not reading about settled questions from the past, but participating in real-time investigation of an active mystery. We get to see the debate unfold, watch evidence accumulate, observe how scientific thinking evolves in response to new data. It's messy and uncertain and sometimes frustrating, but it's also authentic and alive in ways that polished textbook accounts can never capture. and there's value in that authenticity, it reminds us that knowledge is hard-won, that understanding emerges from dedicated effort, that discovery requires patience and rigour, and the courage to question assumptions. The coming months and years will bring more data, more analysis, and hopefully more clarity about what 3i Atlas actually is. The opportunities to learn are abundant, the tools available are sophisticated, and the motivation is intense. Whatever we ultimately discover will be worth the effort. And the journey of discovery itself, independent of the destination, enriches our collective understanding and demonstrates humanity at its best, curious, rigorous, open-minded, and relentlessly pursuing truth wherever it may lead. With those future opportunities outlined, let's bring this exploration to a close with some final thoughts about what this mystery means and what questions it leaves us with. So where does all this leave us? We've journeyed through the observations, examined the competing interpretations, considered the profound implications and surveyed the path forward, and we're left with a mystery that remains tantalizingly unresolved, a cosmic riddle that continues to challenge our understanding and invite our speculation. 3. Atlas, with its impossible jets and enigmatic ejections, sits at the boundary between the known and the unknown, testing our assumptions about what's possible and what's real. The honest answer to the question, what is 3i Atlas releasing, is that we don't know yet. We have data that's difficult to explain naturally. We have hypotheses, both conventional and extraordinary, that each capture some aspects of the observations but struggle with others. We have passionate advocates for different interpretations, all working with good faith and genuine expertise, reaching different conclusions from the same evidence. This is the reality of science at the frontier: uncertainty, debate, incomplete information, and the hard work of distinguishing between what we want to be true and what the evidence actually supports. What makes this particular mystery so compelling is its position at the intersection of multiple profound questions. It's not just about comet physics or interstellar object composition, though it's certainly about those things. It's about whether we're alone in the universe. It's about how we make sense of observations that challenge established frameworks. It's about the courage required to seriously consider possibilities that seem outlandish, while maintaining the skepticism needed to avoid self-deception. It's about humanity's readiness to confront cosmic realities that would fundamentally change our self-understanding. The tension between these considerations creates the drama we've been exploring. On one side, there's the conservative impulse to exhaust natural explanations before considering exotic alternatives, to maintain high evidentiary standards, to avoid the embarrassment of premature extraordinary claims that later prove wrong. This impulse serves science well, protecting it from flights of fancy and maintaining public trust through demonstrated rigour. On the other side, there's the awareness that genuinely novel discoveries sometimes require breaking from conventional thinking, that revolutionary insights often come from those willing to question orthodoxy, that holding too tightly to established frameworks can blind us to evidence that doesn't fit those frameworks. Both impulses are necessary. Both can be destructive if taken to extremes. Finding the balance is the art of doing science well. 3i Atlas forces us to navigate that balance in real time, with public attention amplifying both the excitement and the pressure. Scientists working on this have to manage not just the technical challenges of observation and analysis, but also the social dynamics of debate, the media interest in controversy, and the responsibility to communicate clearly without overstating certainty. It's a challenging position, and reasonable people are handling it differently, leading to the range of perspectives we've examined. What I hope you take away from this exploration is an appreciation for that complexity. The easy narrative would be to declare confidently that 3i Atlas is either definitely natural or definitely artificial, to pick a side and defend it against all counterarguments. But that's not where the evidence is right now. We're in the messy middle, where honest uncertainty is the only intellectually defensible position. We're acknowledging what we don't know is more important than pretending to have answers we don't actually possess. Living with that uncertainty is uncomfortable, but it's also honest, and honesty is worth more than false certainty. That said, uncertainty doesn't mean all possibilities are equally likely. Based on current evidence, most scientists would still place natural explanations at higher probability than artificial ones, but with less confidence than they would have initially, given how the anomalies have persisted and even strengthened with better observations. The artificial hypothesis remains low probability but not zero probability, and that non-zero assessment is itself significant. Serious scientists are seriously considering a possibility that would once have been dismissed out of hand. The space of plausible explanations has expanded, and that expansion, regardless of where evidence ultimately points, represents a kind of progress. The questions this mystery raises extend beyond the specifics of 3E Atlas. They touch on how we approach cosmic mysteries generally, how we balance skepticism with openness, how we make decisions under uncertainty when the stakes are high. These are questions without simple answers, requiring wisdom more than just technical knowledge, and wisdom emerges from experience, from struggling with hard cases, from learning to hold complexity without collapsing into oversimplification. 3, E Atlas, whatever it turns out to be, is teaching us something about that kind of wisdom. Looking forward, I'm genuinely curious how this will resolve. Will natural explanations eventually click into place, providing satisfying accounts of all the anomalies once we understand interstellar object properties better? Will someone have a breakthrough insight that reframes the observations in a way that makes everything suddenly make sense? Or will the anomalies persist and deepen, gradually pushing even skeptical scientists toward more exotic interpretations? All these outcomes are possible, and each would teach us something valuable about the universe and about how science works. But beyond the specific resolution, I'm interested in what this experience does to us collectively as we grapple with these questions. Are we expanding our capacity to consider possibilities that challenge assumptions? Are we learning to distinguish between healthy skepticism and defensive rejection? Are we developing the intellectual muscles needed to handle genuinely paradigm-challenging discoveries should they occur? These meta-questions about our readiness and our processes might matter as much as the object-level question about what 3i Atlas is releasing. There's also something poetic about the situation we find ourselves in. Here we are, one species on one planet orbiting one star in a galaxy of hundreds of billions of stars, detecting an object that originated somewhere else in that vast expanse, watching it behave in ways that confound our understanding, and asking whether it might represent a message or probe from minds we've never encountered. The very asking of that question, independent of its answer, says something profound about where humanity has arrived in our development. We're capable of detecting interstellar visitors, analysing their properties, considering their implications. That's remarkable, a testament to human curiosity and ingenuity. And yet, we're also still groping in the dark, limited by technology and distance, forced to work with indirect evidence and incomplete data, unable to simply go out and inspect the object up close to settle the question definitively. That's humbling. A reminder that despite our impressive capabilities, we remain small and constrained in a cosmos that doesn't yield its secrets easily. Holding both of those realities together, pride in how far we've come and humility about how much we still don't know, is part of mature cosmic consciousness. So here's what I want to ask you. After everything we've explored together, what do you think is happening with 3i Atlas? Not what do you hope or fear, but what does the evidence suggest to you? Are the natural explanations sufficient, requiring only more time and refinement to fully account for the observations? Or do you sense that something genuinely unusual is occurring, something that might require expanding our categories beyond what we've previously considered? There's no wrong answer here. We're all trying to make sense of ambiguous data pointing in multiple directions. But I'm curious where your intuitions land after examining the evidence and the arguments. I'm also curious about the meta-questions. How much evidence would you need before taking the artificial hypothesis seriously? What would constitute sufficient proof? And conversely, what would convince you definitively that the natural explanation is correct? Thinking through these questions helps clarify our own standards for evidence and our own biases in how we evaluate competing claims. It's valuable self-examination, independent of which interpretation ultimately proves correct. Drop your thoughts in the comments. Tell me whether you think we're looking at exotic natural phenomena or potential technology from beyond Earth. Explain your reasoning. Share what aspects of the evidence you find most compelling or most problematic. Let's have a real conversation about this. Not just cheerleading for preferred conclusions, but genuinely grappling with uncertainty and trying to think clearly about what the data does and doesn't support. That kind of thoughtful engagement is how we collectively make sense of mysteries like this. And if this exploration has sparked your curiosity about the broader questions of life in the universe, about how science investigates extraordinary claims, about the methods we use to distinguish real signals from noise, then I've achieved what I set out to do. These questions matter. They touch something fundamental about human existence and our relationship to the cosmos. Engaging with them seriously, even when definitive answers remain elusive, enriches our thinking and expands our horizons. Whatever 3i Atlas turns out to be, we're living through a moment of genuine mystery. A time when the universe has presented us with a puzzle that we're actively working to solve. That's a privilege. Centuries ago, people could only wonder about the lights in the sky, unable to study them in detail or answer questions about their nature. We're in a fundamentally different position, with tools and knowledge that allow us to investigate cosmic mysteries rigorously, even if we can't always solve them immediately. That ability to investigate, to gather evidence, to test hypotheses, to gradually converge on truth, that's one of humanity's greatest achievements. So stay curious, keep asking questions, demand good evidence, but remain open to surprising answers. Follow the investigation as it unfolds, watching what new observations reveal and how interpretations evolve in response. And most importantly, hold complexity without collapsing into certainty when the evidence doesn't yet warrant it. That intellectual discipline, that willingness to live with uncertainty while actively working to resolve it, is the essence of scientific thinking, and it's a skill worth cultivating, applicable far beyond astronomy, valuable in every domain where we face ambiguous information and competing interpretations. Thank you for taking this journey through the mystery of 3i Atlas with me. Whether this object turns out to be a weird comet or humanity's first encounter with alien technology, the investigation itself has been worthwhile, pushing us to think harder, look closer, and question deeper. And that process of rigorous inquiry, of wrestling with the unknown, of refusing easy answers while remaining committed to finding truth, that's what makes us human at our best. Keep watching the skies, keep asking questions, and keep your mind open to possibilities you might never have imagined, because the universe has a demonstrated tendency to be stranger and more wonderful than our wildest speculation.